Hello everyone, my name is Kyoung-Hee Kim and I am a professor of architecture at UNC Charlotte. Today we will cover heat wave resilience in the built environment. As we discussed in the introductory video, global warming is increasing, and we are facing more frequent and severe heat waves around the world. In this lecture, we will explore how architectural design strategies can be incorporated to resist extreme heat waves and protect both human health and comfort, as well as the built environment. This slide presents a global map of countries and the highest temperature recorded in recent years. Almost all geographic regions around the world have reached unprecedented high temperatures. Extreme heat waves are not confined to local areas, but rather affect every part of the Earth. When we look at local areas, extreme heat exposure is not equal for everyone. The pie graphs above predict heatwave exposure in billions of people per year for different income groups in the 2030s, 2060s, and 2090s, respectively. They show that lower income populations highlighted in orange are expected to experience far greater heat waves than high income populations. This may be because their communities lack green spaces, or they cannot afford access to air conditioning equipment. The world map in this slide shows heat stress experienced by populations across the globe. The global south is shown in red, including South Asia, Sub-Saharan Africa, and some areas of Central and South America, are affected by more frequent and extreme heat than high-income countries shown in green. These lower-income areas have high population density and lack adequate climate control systems. Exposures to high heat stress lead to increased vulnerability to health hazards and property damage. On the other hand, high-income regions experience less heat stress because they receive greater protection in their buildings and sites. This environmental injustice reveals that global warming is an additional contributor to furthering social inequality. Therefore, policy and interventions should focus first on safeguarding the most at-risk community and populations. Now let's review heat-resilient design strategies. We have seen this resilient design framework consisting of original state, mitigate, adapt, and recover. Using this framework, how would heat-resilient design align with this framework? First, minimizing heat gain at building and site levels is an essential strategy under mitigate. Heat gain is reduced by blocking unwanted heat that enters interior spaces and minimizing internal heat gain inside. Tree shading or overhangs, window ventilation, and good insulation effectively keep heat out and helps indoor spaces stay cooler naturally. Second, providing energy-efficient cooling systems can be another strategy under adapt. Extreme heatwave conditions will not allow natural cooling of the space and will require an active air conditioner to maintain comfortable indoor temperatures. Third, the integration of a backup power source represents another important feature under recover. Essential systems, along with cooling devices powered by a generator or battery, can remain functional in the event of a utility outage. The risk of a power outage during extremely hot days is significant due to the surges in cooling equipment usage and overloading the utility grid. The following slides will explain each aspect in detail. The first strategy against heatwave conditions is to reduce unwanted heat gains with bioclimatic design strategies. Refer to bioclimate design videos for more details. In summary, this requires shaping the site and building geometry to block and remove unwanted heat. At the building and site level, landscapes and trees around a building will temper the local microclimate through tree shade and evapotranspiration. Limiting the size of the east and west facing windows reduce unwanted solar gain from intense low-angle sun. High-performance windows coupled with effective shading devices such as louvers and fins can block additional sunlight before it reaches the room. Airtight and insulated building envelopes mitigate all three modes of heat transfer caused by conduction, convection, and radiation. High-performance envelopes resist heat absorption during daytime and limit nighttime heat radiation into interior spaces. This helps with good thermal comfort levels at night. Additionally, operable windows, roof vents, or attic ventilation allow natural ventilation through a buoyancy effect to vent hot air from the building. Finally, using high albedo walls and high reflective roofs keeps much of the sun's energy reflected away instead of absorbed. In combination, these measures significantly reduce the heat gain that the building and site must deal with in the first place. Now we turn to integrating energy-efficient cooling systems. This starts with using energy-efficient technology. For example, an energy recovery ventilator, ERV, can pre-cool incoming fresh air by utilizing exhausted conditioned air, saving energy to cool outdoor air. All appliances and artificial lighting systems should be high efficiency to minimize both energy consumption and internal heat gain. Some cooling technologies using ground source heat pump are more energy efficient because they use stable cooler temperatures underground when outside air is very hot. In addition, alternative cooling methods can supplement mechanical air conditioners, including evaporative coolers, night purge, underground pipes, and so on. Integration of backup power for emergency use is another critical feature in resilient building design. If power goes down without a backup power supply, even the best climate control systems become useless. Generators or batteries are typical emergency power systems, which ensure the continuous operation of essential systems. The backup power capacity can be sized based on the power needed to run critical equipment and the duration of backup power use. Additionally, given the increasing frequency of wildfire around the globe, air pollutants and wildfire smoke are important considerations for resilient building design. When such contaminants are present, high-performance air filtration systems should be active to remove pollutants and maintain acceptable air quality. Such systems should be designed to operate so that during the simultaneous occurrence of heat wave and power loss, occupants can stay protected, and the indoor environment can be kept within safe and comfortable conditions. This slide illustrates temperature increases caused by the urban heat island effect. The horizontal axis shows different built environment settings, while the vertical axis represents temperature. The orange solid line shows surface temperatures measured at 4 p.m., while the dotted line shows ambient temperatures measured at the same time. Similarly, the blue solid line shows surface temperatures at 2 a.m., and the dotted line shows the ambient temperatures at the same hour. In the city center, high building density with tall building heights contributes to trapping heat and significantly increases city temperatures, a phenomenon known as the urban heat island effect. During daytime, the surface temperatures of buildings in the city are much higher than those of rural areas due to trapped heat stored in concrete and asphalt surfaces. These low albedo characteristics of these surfaces retain heat during the daytime and gradually release it during the night, still maintaining the high surface temperature. Interestingly, at night, surface temperature and ambient temperature in the city remain high and at similar levels, meaning they reach a steady-state condition. On the other hand, rural and suburban areas as well as locations near ponds and natural landscaping maintain cooler environments due to low-density development and more green spaces. This slide shows an excerpt from a publication regarding heat island inequality. Beyond individual buildings, we must consider equity in heat wave buildings. Excessive heat is a financial burden for many people, especially low-income households. For instance, about 30% of all U.S. households report that they have difficulty paying energy bills or that they are unable to cool their homes due to cost concerns. Low-income households also tend to live in less energy-efficient homes that are more expensive to cool. The inability to afford household energy needs, or energy insecurity, makes it harder to stay cool, comfortable, and healthy during periods of extreme heat. More equitable urban planning and policy support for vulnerable communities are needed. Natural elements such as landscapes, vegetation, and trees are among the most effective, sustainable ways to cool cities. This slide illustrates the cooling effects of evapotranspiration from trees. First of all, tree canopies lower ambient temperatures by blocking sunlight and providing shade. Moist soil for tree roots also cools the air through a process called evaporation. Additionally, water pulled by trees from the soil is released from their leaves through a process called transpiration. These phase changes from water to vapor during evaporation, transpiration, or so-called evapotranspiration help reduce heat. Trees and landscaping elements improve measurable cooling effects in the microclimate. This slide shows the cooling effect from vegetation inside a greenhouse. Using thermal imaging, there is a stark contrast in surface temperatures. The surface temperature of the skylight measures approximately 39 degrees C, whereas trees below the skylight show a much lower surface temperature around 23 degrees C. Slide 14 through 16 present infrared camera images showing the surface temperatures of non-pervious materials. The significant temperature difference is due to the green roof's vegetation and soil, which absorbs much less heat and cools the surrounding air through evaporation and transpiration. This thermal image indicates that the non-vegetated roof under the summer sun often reaches surface temperatures of around 65 degrees C, whereas the green roof records surface temperatures of approximately 25 degrees C. The surface temperature difference between the non-green roof and green roofs is around 40 degrees C. This slide shows another thermal image of a non-vegetated roof. A conventional roof can reach surface temperatures of up to 80 degrees C. City streets are primarily covered with concrete and asphalt. These low albedo materials enable them to easily retain solar heat and increase surface temperatures. As a result, they can reach surface temperatures of 67 degrees C on a hot afternoon as shown in this slide, and radiate heat back to the surrounding area. This heat wave radiating from street surfaces worsens extreme ambient heat environments. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Let's continue to innovate resilient built environments.